Today I'd like to talk about having fun with planetaries. The objective is to first look at the planetary gear train that was used in the original 3-speed automatic transmissions for vehicles. Next, we want to take that and generalize it to see how those planetary gearheads can be used on servo motors. And then we want to kind of peek in and look at some internal stuff within those planetary gearheads of servo motors. So the first thing is we're going to take a look at this How Stuff Works website that talks about the original automatic transmission. Here you can see some of the components of an actual automatic transmission. You can see the ring gear. Here you can see the internal teeth of the ring gear. This is a planet carrier, and you can see some planets here, and then you can see a sun gear in the middle. So this is sort of taken apart so you can see the parts, and this is actually a compound planetary as well. What we're going to take a look at is just a simplified type. If you go look at this website, you're going to see something like this, where they go through an actual example of a simple planetary gearhead, and it has a ring gear with 72 teeth and a sun gear with 30 teeth, and they go through and they actually calculate some gear ratios, and we want to go through and see how does this make sense. The How Stuff Works website has a very nice animation that relies on showing the various components. The ring is shown as blue, the sun in the center is shown as orange, three of the planets are shown as green, and the fourth planet is shown as brown. The planet carrier, or the arm, is shown in purple, and they show you that it's a sequence of selecting something as being your input and another thing is being your output while you're fixing something. So it's a sequence. Shifting through the gears by the automatic transmission is a sequence of doing that. So let's take a look at maybe the first one, where the sun is the input. The output is going to be the planet carrier, purple, and then the ring is going to be stationary. So let's see what happens there. Okay, so as you can see, the sun is turning clockwise pretty quickly compared to what the planet carrier in purple is doing. And in fact, it's rotating 3.4 times faster, the sun is, with respect to the planet carrier, and they're both going clockwise. That's actually going to be your biggest reduction, and that's actually first gear. The next one is where the sun remains your input. The ring is actually going to be your output, and the planet carrier is stationary. So the purple thing is held fixed, and the ring is rotating counterclockwise while the sun is rotating clockwise. So they're rotating in different directions. The sun, you can tell, is going faster than the ring, and it's going faster by 2.4 times. So that's second gear. And then third gear is where the sun is actually stationary, the planet carrier is the input, and the ring is going to be your output. So planet carrier, they're both going in clockwise direction. The planet carrier is your input. If you notice, it may take a few seconds to realize it, but the ring output is actually going a little bit faster than the input, and this is an overdrive that's happening in our highest gear. What I'd like to do is delve into some detail of how these gear ratios come about from these calculations. So sort of go and do some background theory here. As I was saying, the first gear is actually the highest reduction, the 3.4, and the website is showing a calculation like this based on the number of teeth in the ring and the number of teeth on the sun. Second gear is going to be the minus 2.4 to 1. A little bit less of a reduction, so that's your second gear. The negative sign there really means that we would need like an idler to reverse that back so that we continue to go in the forward direction. And then the third gear is the highest gear, and we want to know why these calculations are correct. That's what we're going to go study right now. So let's take a look at a kinematic diagram simplified. For the purposes of kinematic, we really just need one planet. So I'm going to show one planet as body 4. Body 1 is the case. 2 is in the center, is the sun. The arm or the planet carrier is 3, body 3, and then the ring is body 5. So that's our kinematic diagram that we're going to be studying. In the Shigley book, we looked at train value, and for train value here, we want to think about link 3 being fixed, and we want to think about what's happening in the gear train, starting with the sun, the planet, and then the ring. So in the train value, we have a product of all of our driving gears on the top. And then we have the number of external meshes is the minus 1 to the m. So we have m external meshes, if you remember. So here we just have one external mesh between the sun and the planet. The planet and the ring is actually an internal external. So we don't count that. We just have one external mesh. Driving gears, we've got the sun driving the planet, and then we have the planet actually driving the ring. And then you divide by the product of the driven gear teeth numbers. So the planet is being driven by the sun, and then of course the ring is being driven by the planet. And that's what we end up showing here is our driving gears are S is the sun, P is the planet, because the planet drives the ring, as I said, and then you're dividing by the driven gears, so the planet is being driven by the sun, and then the ring is being driven by the planet. Of course, the planets cancel, and you just have the 1 minus sign. So the train value is the sun, number of teeth on the sun, divided by the number of teeth on the ring. So it's pretty straightforward from our Shigley stuff. Also, when we were looking at the train value, we know that it is going to be the speed of, so lowercase n here is the speed in RPM of, in this case, the ring 5 divided by the sun 2. So we know that. That's the ratio of the output to input speeds for the train value. Output to input. And then we're going to bring back what we found on that website, try to make sense of this. And we're going to focus on the last row, which is where the planet carrier or the arm is fixed. That's what we have here. And from that definition of what the gear ratio might be of that last gear, it's going to be the input speed, which is the sun, N2, divided by the ring, which is the output, N5. So the ratio of input to output speeds would be that G sub C, or the gear ratio of that last row. So we want to resolve these. And when I bring in in this example, the sun is 30 and the ring is 72. When I bring that in, we actually can calculate what the train value would be. We simplify it's minus 5/12. And then if you pick up that the train value is actually equal to the reciprocal of the gear ratio, then you could just say that the gear ratio is equal to 1 over E, and that's going to be minus R over S. And then we can bring in the numerical example being minus 12 over 5. And you know what? That's equal to minus 2.4, which is the gear ratio that they said in the example. And they also have for calculation minus R over S is equal to the gear ratio. So you know what? This is actually correct. So that's very nice. So we've satisfied or shown that the last column, or I'm sorry, the last row C, which is actually our second gear, is going to be correct. So we understand that. So let's take a look at row A. Well, row A, we have the sun as the input, so it's defined as N2 and the planet carrier body 3, N3 is going to be our output. So the gear ratio would be defined as N2 over N3. What we can do is we can go back and we can sort of relax what our train value was defined as. We can say that's actually equal to a ratio of relative angular speeds. So we could say instead of N5 over N2, we could actually say N5 minus N3 divided by N2 minus N3. And this still would be what we had before when N3 would have been 0. So it's still the same, still consistent. Just now we're gonna free up the arm because we need to. So for row A, the ring is actually fixed in row A. So I'm going to let N5 equal 0 in this equation. So I substitute 0 for N5. And then I said, well, why not divide through top and bottom by N3? Because I'm looking over here and I want to have N3, want to be able to make a substitution later. So I divide through by N3. When I do that, this simplifies to 1 and 1, and I end up with, look at there, that is my GA right there. So I've got what I need, and then basically I can take my GA, take this equation and solve for GA. So my GA is 1 minus 1 over E from this. And then I can substitute what my E is. Remember, 1 over E is minus R over S. So I can make that substitution. This GA being 1 plus R over S, that's what we had here. When I make the substitution for R over S, I end up with double negative, and I end up with basically 1 plus 2.4 or 3.4. And you know what? That is a numerical example that they had, 3.4 to 1, and that was our first gear. So you know what? This is correct. So the next one we take a look at, we're going to sort of repeat what we just did. And here we're going to look at our what would be our third gear, our row B. We're going to let our planet carrier, and that would be the arm, N3 be our input speed, and then our output speed is the ring, N5. So this is the ratio that we're looking for. So we're going to go back here and we're going to say, well, the sun is, which one is fixed? Stationary, the sun is fixed. So we're going to, in this relation, we're going to let N2 be 0. And then we're going to divide through by N5 because this is sort of guiding us. When I do that, I end up with GB being there and there. And I can really take this and run with it and solve for GB as a function of E. And that's what I do. I solve for GB. I get 1 over 1 minus E. And then, of course, I can substitute back in the value I had for my train value, E. And I end up with 1 over 1 plus S over R. Hey, you know what? That's what they had here in their calculation. When I make my substitution for S over R, I end up with GB equal to about 0.71. And that's the overdrive that we had before. So this works out again. So we've kind of gone through some of the stuff that we knew before from dealing with gear trains. and gear tooth numbers, and this all makes sense for the planetaries. So that's really nice. What I'd like to do now is to transition our discussion into the planetary gearheads that we were using on our brush style DC motor, the 15 millimeter diameter motor that we used earlier on our gripper project. And this was a very small planetary gearhead, the 15 millimeter that we had before. All we knew before that it was a 3-stage 69-to-1 gearhead that looked like this, that we attached to our motor. We want to get a feel for how this looked and sort of get a feel for how the loads propagate through. 3-stage planetary gearhead. Here is my SolidWorks rendering of that planetary gearhead. Actually used the US customary dimetral pitch method rather than the module method. That's what I'm going to talk about today. And tried to get it about the same size as 15 millimeter. Let's see if I can show you what my outside dimension is here. So it looks like 0.58. That's just under 15 millimeters if you check it out. But you can clearly see that I've got a ring that carries through all 3 stages. So my ring is actually going to be my fixed element. It's obviously attached to the case. My motor is back here, and it's actually going to be turning the sun. So my inputs are sun. The planets are going to be rotating around, and my output of, say, the first stage you're looking at here, the output is actually going to be the planet carrier. Let's take a look at that. And if we kind of look at what our strategy was from our automatic transmission, the biggest gear ratio or reduction came about by letting this input be the sun, letting the ring be stationary, and letting the output be the planet carrier. So I actually used that 3 times. So the sun of the first stage is connected to the motor, and that forms the input for the first stage. As I said, the ring is stationary, and then the arm carrier is actually going to be the output of the first stage. And I can show you what that arm, the carrier, looks like. Here is that particular scabbed up arm carrier, planet carrier. This over here is where the planets from the previous stage rotate. And then the output here is where the sun of the subsequent stage or the next stage would be locked. And how I do it in SolidWorks is I take the next sun and I lock the top plane of the next sun to the top plane of this body so that those are connected together. So if I kind of zoom around here, maybe I can show you that. So that's what it looks like. I'm going to try to highlight the next stage. Maybe I could hide that. And then that's the next stage 2 pinion. And if I look at the mates of the stage 2 pinion, it's concentric. There's a coincident mate there. And then there's the right plane, I guess, of the next pinion is mated to the top plane of the take a look at that. Yeah. So the right plane of the arm is going to be mated to the plane of that pinion, of the stage 2 pinion. So that's how I do it. I just lock those planes together so that you know that the sun of the second stage is locked to the arm carrier of the first stage. You can see here that the sun of the input stage, when the motor is rotating much faster, you can see that the second stage sun is rotating with the arm carrier of the first stage. And you can see as I move it that progressively the stages move slower and slower. The second stage has 2 planets. Actually, because as the load increases, I actually included 4 or put 4 pinions on the output stage. And if you look, the face widths of the output stage is actually a little bit more. So that's something I'm going to step through with you momentarily. And then the final stage, the arm carrier of the last stage, is the output shaft. And I have just a little nub here just to show that it is rotating. It's kind of hard to tell if it's rotating otherwise. So anyway, so that's what this looks like. I'm going to show that again. Okay. The next thing I wanted to discuss with you was the choice of gear tooth numbers that I used in my planetary gearhead. I used on the ring, I used 62 teeth. On the sun, I used 20. And on the planet, I used 21. And it was important that these tooth numbers work out so that their diameters would allow this to be a planetary. For a planetary, 2 times the planet diameter plus the sun diameter must equal the internal ring diameter. And if you look at all these gears having the same diametral pitch, what that means is that 2 times the number of teeth on your planet plus the number of teeth on your sun, that would have to equal the number of teeth on your ring. So these have to be compatible, and they are. I use the same gear tooth numbers for each stage. And if I look at what my gear ratio is, if you remember, when the ring is fixed, the gear ratio is 1 plus the ring divided by the sun. And that's 4.1 in this case. So the overall gear ratio would be basically 4.1 cubed, or 4.1 times 4.1 times 4.1. It's very close to 69, and I suspect that that particular gearhead is estimated at 69.1. It's not exactly 69.1. So as far as I know, but this is very, very close. If I go look 4.1, if I go back and take a peek at my implementation here, so the sun's 20, planet 21, ring 62, and I actually used, if you go back and look at my layout here, I actually used the toolbox to create all of these gears. I used a 120 diametral pitch, 62 teeth on my ring, internal spur. So very quickly I was able to do this. The whole thing may have taken me a couple hours to kind of scab together. Planet, 21 teeth. Sun, where's my first sun? Motor pinion, 20 teeth. So there we go. And if I were to take and rotate my motor one complete rev, I think you'll see that the planet may move a quarter of a turn roughly. So I'm going to try that. I'm going to try to go, yeah, it went about a quarter. If I go 2, 3, 4, I get the planet carrier back to where it was roughly. So that's how the gear teeth kind of worked out. And what I thought I would do with the remainder of our discussion is to take a look at sizing those very small teeth and very small gears, I chose a diametral pitch of 120, and I did that so that this diameter here would work out to be the diameter of the ring would work out to be a little bit less than 15 millimeter, and it is 13 and something there, and that allows me to have a case around that. So this is very realistic. So what I'm going to show you now is the beginning of chapter 14, where we're looking at the Lewis bending stress calculation, and I'm actually going to use it to calculate what the face widths need to be for the various stages. My first stage, if you remember in my previous discussion, I had that first stage from the motor providing or accepting a 5.14 millinewton meter load going through that, and then I propagated those torques into the various stages. So the blue stage is your first stage, green is second, and the third stage I've got is pink shown. And what I did is wrote down the diametral pitch being the same all throughout, and then I wrote down the number of teeth on the gears, the sun, the planet, and the ring, and then I calculated using the diametral pitch and the number of teeth. I calculated the various diameters in inches. We'll come back to this Lewis in a minute. And then I had the number of planets here for each stage. So the first stage had 2 planets. And then I calculated, if you remember, the working load, the tangential working load. I calculated that as the torque. And then I have this 113, that's that transition from millinewton meters to inch pounds. So I have millinewton meters now shown in inch pounds, and I'm dividing by F35, so that is the number of planets, and then I'm dividing by E35 divided by 2, so that's actually the radius. So this is representative of what the tangential working force would be for that particular gear. And this sort of says that the working force is carried by one tooth. And you know what? In chapter 13 they talked about contact ratio. We may actually have more than one tooth carrying the load, so this is a little bit conservative here. So I have that WT in there in a conservative way. We're making plastic gears, so I've chosen a yield strength for plastic. I have a design factor of 1.25, and I'm going to go in and show you a little bit of background here, but I calculate a Lewis face width. In order to get this, I have to kind of come down to the bottom equation here to bring in the Lewis bending equation. And it looks like this. The Lewis bending stress is related to the tangential working load. It's related to the diametral pitch P, capital P. It has F is the face width. Y is this Lewis form factor. We actually have to go grab that Lewis form factor. I'll show you that in a second from table 14.2. That's what I populated this column with, is the Lewis form factor from table 14.2. It looks like this: 20 teeth, 21 teeth, so we need those. And there's the 60 teeth. So I'm going to set this all equal to the yield strength divided by the design factor. If I take this relation here and solve for my face width, I really want to know how fat a face I need on my gear in order to keep this relation happy, quote unquote happy. And that's what I do. I solve for F and then say, well, if F is bigger than that, I'm good. And let's see what this is. So if I pick that one row, it's showing I35, so that's the ND. It's showing G35, so that's the working tangential force. Then it's showing B35, so that's the diametral pitch, and it's dividing by quantities. D35 is the Lewis bending form factor, and H35 would be the yield strength. So these values are very small. And then when you read chapter 14, it says, you should really always use at least three times the circular pitch. This is lowercase p. So this is what I calculated here. So I had to take the diametral pitch and divide that into pi to get the circular pitch. If you remember your lowercase circular pitch, lowercase p. So 3 times that would be 79 mils, or 79 thousandths of an inch. So you get a feel for what your minimum should be. And then I went through and calculated each stage. And remember, on the output stage, torque gets kind of big. So I actually had 4 planets for that. And from the Lewis face width, I get something that starts to be a little more substantial, and actually go fatter on that. And that's what I showed you on that one SolidWorks view. So the first stages, 85 mil is what I ended up using, and then I used 110 mil on that last stage. Let's go check that. So I zoom in here, measure. I'm going to try to pick up that edge. So that's the face width. Oh, I don't know what this is. Get rid of that. Delete. Yeah, so 85 mil on that first stage. I'm going to go over here and see if I can sneak a peek at this output stage here. 110. So that's what I used on that output stage for the fatter output gear carrying the more load. So that's how you can size gears. So I wanted to give you that as well. So in summary, I feel like we've mastered the kinematics of the Planetary gear train. We saw some multi-stage Planetary gearheads, how they're used in servo motors. And then finally, we used the Lewis bending stress relation to size the face widths of those gears. Hope you've enjoyed.